All right, benzoic acids. Fancy new name, benzoic acid. It's just because there's a benzene ring next to the carboxylic acid, but same process, okay? So don't get distracted by the fancy name. Um, so again, if we're thinking about which of these is the stronger acid, and again, this is from page 5 of your note packet. I even left off the one in the middle. If there's the one in the middle is benzoic acid by itself. It doesn't have any substituent. So you'll kind of see how that one would work based on these two. Which of these is the stronger acid? Well, which of them has the more stable conjugate base? So if there was some type of base that stole a proton from this, that would make two conjugate bases. One would look like this. And then this one looks the exact same, but it just has the nitro group. So at this point, I would urge you to pause the video for a minute and try to decide how these substituents either stabilize or destabilize the carboxylate anion. So how do they impact this CO2 minus? You should be able to figure that out based on how the substituent ties in with that arene ring. So again, pause it for a minute and then come back. Okay, you've done that. That's great. Essentially we have two different types of groups, right? This is an electron withdrawing group. This is an electron withdrawing group. This is an electron donating group. So this has two lone pairs that can be fed into that ring system. Hopefully you already drew some structures to show what you think, how you think those substituents impact the ring and how they impact that O minus. But I'm going to show the ones that kind of show it the most extreme, I guess I'd say. So if we show that these electrons can be pushed into that benzene ring, then this pi bond can move over here to make a pi bond between those two. Then this pi bond can actually come to this position. We then see that essentially the negative charge, the lone pair, is going to be directly adjacent to that CO2 minus moiety. So what does that look like? We would have a lone pair and a negative charge right next to that O minus. So this is going to be really destabilizing, having a negative charge, a full negative, right next to another negative. And technically, I guess this isn't a full negative, right? Because we have to average out all of the resonance structures. But we have some negative charge next to negative. That can't be good. Like charges repel. We want a positive by a negative, not a negative by a negative. So how does this group differ? This group differs because this is an electron withdrawing group. So we can actually show those electrons come up to that oxygen, that pi bond going and making a pi bond between the carbon and the nitrogen, this pi bond coming over, and then that would leave this carbon lacking a valence shell, and it would be positively charged as a result. So how does that look? There's a positive charge there. That should be positive. And there is the full structure. So here we have a positive. I'm going to rewrite that in here just to make it abundantly clear. A positive right next to that negative. Remember, what do we want? We want different charges stabilizing one another. That's what we have here. So these stabilize one another. That makes this a more stable conjugate base. So this whole thing is the more stable conjugate base, which makes this the strongest acid. So if we have electron withdrawing groups next to our carboxylate, that stabilizes it. So kind of the same situation we saw with the chlorine in reality. Now it's just tied into this big ring. But essentially, have an electron withdrawing group near carboxylic acid. makes it a stronger acid because it stabilizes that conjugate base. Yeah, that should make sense. Let me know. Okay, so we talked a lot about carboxylic acids, what makes them more acidic than other things. We talked about different types of carboxylic acids, but it turns out that there's something special about this situation too. From first glance, I think a lot of you probably look up here and you say, oh, an alcohol. Oh, an alcohol. Those probably are about the same as far as acidity. Maybe they have the normal pKa of an alcohol, which is 16, right? That's the normal alcohol pKa. But I'm going to tell you right now, one of these two is significantly more acidic than the other. It's actually 10 to the 6 times more acidic than the other. Which one of these is more acidic? So pause the video, think about that for a minute. And you might want to draw some structures to help yourself out. It's just you. All right, I'm back. Okay, so which one's more acidic? How do we figure that out? Look at the stability of the, you said it, conjugate base. Okay, so we're going to draw the conjugate bases in here. Got our O minus right there. O minus right there. All right, here we go. We got our conjugate bases. They look the same, right? We got oxygen that's negatively charged. Same atom. Is there anything special about either of them? Anyone see anything? Oh, yeah. One of these is conjugated. Yeah, great. So this negative charge right here is adjacent to a bunch of pi bonds in that ring. That means that those electrons are going to be delocalized through the ring structure. And we're going to draw one of those structures anyway. So we have the electrons moving there and there. That puts the negative charge on that carbon. So we have the negative charge right there. But also it could theoretically move to that position and that position. If you're having a hard time seeing that, practice, draw these resonance structures. Organic chemists often need to draw as much as they need to think to really reinforce the content. So make sure you're drawing these things out. But essentially, with this OH, it has an anion for the conjugate base that isn't just on the oxygen. It's on the oxygen, on that carbon, and on that carbon. So it's a more delocalized, more stable conjugate base, which means that this is the stronger acid. Turns out that this type of alcohol actually has a name. This is called a phenyl ring sometime, right? We talked about that in the aromaticity chapter. A phenyl ring is just a benzene ring. This type of alcohol is called a phenol, Phenol. Phenols are extra acidic because of that stability of the conjugate base due to that conjugation. Phenols have pKa's of about 10, whereas normal alcohols have pKa's around 16. So 6 pKa units difference, that means that this is 10 to the 6 times more acidic than that. So again, we have to always be thinking about what can stabilize the conjugate base. And that will help us evaluate the acidity of things. So hopefully that makes sense. Let me know if you have questions, and we'll talk some more.